Well. Um, Good after morning. It's still morning still. So, how's it going, everybody? It is alephmuvt coming in today. We have a very special occasion today. We are going to be talking about a very interesting topic today. So, I am very excited. I studied extra hard this week to get this project going, and I am also very excited because this is one of my first YouTube focused streams as well. So I also have YouTube chat open for once. It actually does work. So let's go ahead and get a attendance going on here. So I already see Gauss. What's up? How's it going? Egaz, hello. Ryler, hello. Nep, hi Nep. Karmamos, let's see, and then a few more probably lingering. Komi, hi Komi, and then probably even more. So today I'm waiting for Z to get her intro done first, and then whenever she's ready, then I will be on the side as well. So maybe I should explain. I am very excited about this topic because oh, she's about to get it. Yeah, okay, we're ready to go. Okay. Yeah, hi, hello. Hold on, let me get you over to the correct side of my stream because I kind of did something separate. Oh, you could see me this entire time? I'm so sorry. Yeah, no, it's all good. That's the scuff. That's the live scuff that we want, right? And then let me also bring you up as well. So, Z, go ahead and say hello. And then I think.
Hello. Hello.
All right. Should I introduce myself?
Yes, please go ahead.
Oh, I think you're also like incredibly loud. One more check. I'm sorry.
Hello. Testing.
That's good.
Okay, great.
All right. Hello everybody. I'm alephmuvt. I am a Fractal Math VTuber. I had recently just debuted about a month ago on Pi Day. I am a mathematician, a computer scientist, and did some physics on the side. And I am very excited to bring you guys be a guest on Z's side of things. I also do 3D art and animation, and that is you might have seen some of my animation work with in the channel. Z was very generous to let me play with it, so I'm very excited. And not to spoil anything, but there's probably something in the slides we have today, huh?
All right. Let me know if the audio is good. But yes, someone says it's really loud. Let me know if the sound is loud and clear. Okay, I guess that's good. Well, yes, no, Aleph, you are incredibly talented at Blender. I remember like the first time you contacted me, you were like, oh, like I've been playing with like some Blender stuff. Like, do you mind if I play with your model? And I was like, okay, sure. And then you just like cooked up these like masterpieces, and I was like absolutely caught off guard. It was absolutely amazing.
Oh, yeah, I mean, I can only do it because I got to play with Blender a lot. It was my hobby during the pandemic. So, I would say it literally, the math made sense once I took one computer graphics class. And after that, I was like, you know what? I can try it. I can do it. I can do it.
That's such a cool hobby, though. That's literally such a That's such a like cool hobby to have though. I feel like during COVID, like all I did was like learn K-pop dances. Do anything
Really?
practical. Yeah.
That's cool. I mean, hey, you know what? At least you were, moving around and exercising, right? That's really fun.
I was definitely active. It was a great time. It was a great time for real.
Nice. I was not. So,
Well, I'm so glad that you were finally able to join me as a guest. I know we were planning something out for the longest time, and I just feel like this gravitational wave stuff is like the perfect like balance between like math and astrophysics.
I know this is also going to be a very interesting topic on the math side. So, but yes, you are right. Getting a hold of you is kind of like detecting a gravitational wave. So, it is a chore.
Wait, that's so funny. I think also recently, like, I was hoping to be streaming more, but yeah, I guess there's been a lot of comments about like how bad I sound right now. Yeah, no, I have to admit, like 2 days ago, I was like in and out of consciousness, like napping every like 3 seconds. And so I'm really glad that like my voice is recovered enough for us to finally make this happen.
I'm happy you're alive enough. So we'll make do with the way
Yeah.
you can. Okay, if you need to leave, you'll rest for the rest of the week, right? So
Yeah, no, I have nothing planned this weekend, so I am going to sleep.
yep, same here. I very much plan for this, and I am very excited to take a break. So
Yes, this is going to be great. Well, I have the slides up and ready if you want to get started.
yep, let's go ahead and start with our first slide. Then this is gonna be yours, I think.
Yes, let me pull this up. Okay, cool. So, all right, so I wanted to start off by talking about why general relativity. And I have to admit, like, if we were to do a stream on general relativity, this stream would literally be like a whole day long. Um, and so I'm going to be giving a very quick crash course. And I know, Aleph, you've also added some slides dealing in to the math of general relativity. Um, and so we're going to talk about why do we move beyond Newtonian gravity in the first place. So the goal of moving beyond Newtonian gravity is that we want to connect gravity to the geometry of space-time. And that's because Newtonian gravity makes some pretty big assumptions. It makes assumptions like there's absolute space and absolute time, and that clashes with some ideas of relativity and the constancy of speed of light. I guess what's also shown here in the figure, which I'll move over here, is showing that Newton imagined space to be very fixed, whereas Einstein imagined space-time to be very flexible, and we'll be talking about that more in a second. And what you can actually implement these for is that you can actually apply these ideas of bendy space-time to point masses like black holes, or even apply it to the whole universe as an expansion. We won't have time to cover this today, but one really cool exercise that I really love to show like students is you can calculate how long the universe will last based off of these equations of space-time. And that's because we have these ideas of expansion and gravity, and you can actually measure the time in which the universe would potentially collapse back in on itself for different scenarios, like a flat universe or a closed universe.
Oh, really?
Yeah. And so this is just one application of why we need to move beyond Newtonian gravity. But basically, when we're dealing with these really massive things in space, Newtonian gravity's assumptions simply don't work anymore. And so, Aleph, it looks like it's your slide for the general history of general relativity.
Yeah, this is gonna be a very, very exciting, right? So, I mean, I understand that like on the physics side of things, there's usually a lot of context. So I'm gonna go over to our mathematics slide real quick, okay? So physicists usually get all of the, oh, this very important person started this experiment. And then that experiment led to this discovery. And then we started building more instruments to build more things. And then you guys have lots of data collected, and then you start doing analysis on them all, right? That is not necessarily true. You don't get as much context for the mathematics. So that's why I wanted to cover today. So we have to discuss what math actually existed. Like, it's not just that they were all by themselves, the physicists, I mean. There's definitely a lot of math pretext to let anything happen. Mostly stuff with the differential, with curved geometries, non-Euclidean geometries, and I have to move chat out of the way just to show that off quick. Things after Newton invented calculus, and I believe somebody else, you started learning about the related rates of things, and for especially things like the curvature of like the Earth, you want to discover geodesics and stuff. So that math started developing in around the 1600s and had been continuing development until, it's not that it doesn't stop, it just like this is the most significant portion of it. Afterwards, you discover tensor calculus. Tensor calculus can be described as the most abstract way of talking about calculus. It is like, and you probably will know, right? See if you can
It's
contribute.
very abstract for sure, and there's just so much crazy notation.
So, I mean, I wanted to show off the one that you remember right here. This is the Dirac delta tensor. Sorry, correction, the Kronecker delta. Dirac delta is different. So Kronecker delta is considered a tensor. It is a 1-1 tensor. Whoop-de-whoop. But tensor calculus is the language of general relativity. You cannot get away from this. You have to talk about these weird little Greek letters and stuff, mu and nu and all that. And then the official term for the whole field of curvature mathematics is differential geometry. So that uses stuff describing smooth manifolds and using calculus and linear algebra, as well as measure. Measure is a very big deal with that. And then tensor is if we could describe what a tensor is, let's say we have a number, and then we have a list, right? And then after that we have a matrix, and then a tensor is a bigger list of things. It's the immediate next step to matrices, I guess, right? One of the biggest deals is like always describing what does tensor mean, and even I don't know sometimes. It's so frustrating. But I do have a joke on the next slide. Okay, so some very important tensor people. Probably heard of Ricci. Probably heard of 𝖈𝖗𝖊𝖉𝖎𝖙𝖘.
Yes.
So let's take a look.
𝖈𝖗𝖉𝖉𝖎𝖙𝖘. I absolutely love that. That's like a very special symbol in tensor calculus for sure.
Let's take a look at the next slide, the joke here, because I had just recently played Mahjong as a collab stream with another math VTuber. I was very much inclined to mention this because there is a term in Mahjong that says that you shout when you're one away from winning. So what did the tensor say when it was playing Mahjong?
Oh, wait, this is the...
Ricci!
This is like Uno almost.
Basically,
That's so peak.
It literally is like Uno. So I can't express that this joke will not happen unless it was like literally stars aligned. So hey, pretty nice. Let's go ahead and move on to the next slide then. It was just a joke, really funny. So I do want to talk about this gentleman right here. Physicists do happen to have a lot of mathematics. However, they are not usually exposed to it as much unless they're introduced to it to a friend or a colleague. Nowadays we have the internet, and you could always do things by yourself, or another colleague will tell you what to do. Einstein was in his own league. However, he did not know about differential geometry. Without his colleague and classmate from another time. This here is Marcel Grossmann. He introduced Einstein to differential geometry in about 1913, actually. So that is a very important year, because not long after, when did Einstein develop his general relativity equations? Pop quiz.
Wait, when was that?
I will say it because it's funny. It is literally 2 years later.
That's crazy.
2 years later, he developed the general relativity dogma. So it is very fascinating.
Wait, I did not know any of this history. This is really cool. I also did not know about this Marcel Grossmann person at all. I feel like it's so interesting to see this chain of mentorship and how it's, evolved these minds that have brought us basically the foundations for everything we know today. That's super cool.
It is really cool. And again, we don't mention it too much because at least on the math side, you are more than satisfied if you happen to get your name into anything, right? So yeah. It is really cool. And then physicists, there's a big old thing on why Einstein is so important. But I do want to kick him down a peg just a sec, because I want to contextualize. The math existed by the late 1800s, early 1900s, and then Einstein was doing his own thing before he was even introduced to it, and then he puts it together.
Wow. So we got a question in chat. Maybe you could give some insights to this. Well, first, I found out that it isn't 𝖈𝖉𝖉𝖕 symbol, but it's 𝖈𝖉𝖉𝖉𝖕.
Yeah, it's I think Italian, so they say, cello.
I did not know that. I've been pronouncing that wrong my whole life. But we also did get a lot of questions about what is a tensor? How does it differ from a vector? Or are they just extensions of matrices to n dimensions?
That is a good question. As far as I understand, tensors are what you do. You all the indices and stuff are describing multi-dimensional matrices, I suppose. because you're keeping track of a lot of things, especially coordinate systems, in these equations. It is very important to keep track of it in some capacity, and so when you do, it is just about important. They are like scalars with magnitudes, vectors, and then we have, of course, tensors that describe relationships of vectors.
Yeah, so I guess like typically I like to think like vectors are kind of like a arrow with like a direction and magnitude, right? Like if you think about velocity or force, but a tensor can map more complex relationships. Like for instance, there's something called the stress tensor, which describes like the stresses on an object. And something like that, you wouldn't say that there's like a direction and a magnitude, right? But it's sort of similar in a sense that it describes a physical property. So yeah, lots of great questions, and feel free to keep asking questions. And we'll see if we can get to as many as we can. So yeah.
Yeah. All right. Let's go ahead and move on to the next slide then. Uh, I do have a meme here again, but it is a great meme. So, do you
This
do
is
you
so peak.
do you believe in gravity?
Why are you talking like that?
Do you believe in gravity? The supernatural force that attracts others to. So I only say that because Einstein did not believe in gravity waves, gravitational waves. Because in 1916, a year after he discovered his general relativity equations, he linearized them in a way that made it easy to work with, right? We were working with differential equations, all these wacky things. The math gets really complicated, so he said, let's make it a lot simpler. And when he did that, that would describe the idea of gravitational waves, something that we can barely detect. And so far, he didn't believe them to be real. In fact, even later on in about 1937, with the description of cylindrical curvature space, he
Mhm.
still wasn't convinced. He was still thought that they were just non-physical objects, then ideas, right? Oopsies! Whoa, whoa, whoa! I slipped out my slideshow. So
Mhm.
yeah, and then eventually Einstein had died. Womp womp. But the reason why
Oh,
that's a big deal is
crazy.
because of Einstein's skepticism. The community did not think of it to be as significant. It was it was a big deal at the time. So if he was like the first person really like focusing on this field and everybody else is contributing in some capacity and he says no, everyone else isn't going to try to dare to like contradict him, or his words had a lot of weight, so he died. And for some reason, also, this is completely coincidental as well, though. Let's go ahead and move on to the next slide right here. um Gravitational research just started booming, like out of nowhere. It is just a bunch of coincidences at the same time. It's just really funny to contextualize it as Einstein had died and everyone had a party. So,
Oh, so that's why there's a smiley face after Einstein died.
I'm not
I was
happy.
gonna say, I was like, that's crazy. That's such a crazy reaction to that, but alas.
If it makes more sense, yes, that's why. It's not because I am, I like it when physicists die. That is crazy. Uh,
Hopefully not. Hopefully not. Hopefully none of us die.
yeah. Um,
I mean, if I died, I hope you guys won't be happy about that.
it would be
Uh
Major Bumsville, right? It's okay. I'm hoping that when I die, I have something with my name on it, and I live forever in that regard. Yay!
Amen to that. Amen to that. Yeah.
So research boomed because of several significant factors. So Einstein dies in 1955. A few years before, they had proven that gravitational waves carry energy between the 50s and the 60s. That is the work of Pirani, Bondi, and Robinson. Um, and then right after that, we started getting proper descriptions of the theory. Okay, we were not
Mhm.
about to start doing experimental physics unless the theory was down and really justified the case. So uh that is a big deal about what Einstein had said. He's like, we're not even gonna like start playing with these because they like seemed like statistically impossible to like detect, and they just seem so dumb and stupid until they proved that it is easier to describe them. So that is the work of space-time classification stuff. So are you familiar with how black holes are just referred to as like N type, O type, one type, two type, stuff like that?
No, I'm not. Oh, what do you mean? And what? What?
So,
No.
so those are Petrov classifications. That was important.
Oh.
for describing the context for the differential geometry. It is important that they had some descriptor of of the the phenomena, and they were able to like work with the calculus of it all. So that is the work of Petrov and Penrose. And you probably are familiar with Penrose diagrams. And let me
Yes.
and so that is N type, P type, N type, O type, all that stuff. Uh,
Oh, wait, that's crazy. Actually, one of my first videos on my YouTube channel was to describe black holes and using Penrose diagrams.
mhm. So that came
That's super
about
cool.
during the 50s and then 60s to different individuals. Uh, Following that, there was actual real experimental evidence of gravitational waves because of the binary pulsar discovery by Holst-Taylor. And then, so are you familiar with this end? Because I am.
Yes.
Yeah, so it is actual evidence describing it, not just the evidence of the general relativity, because that's been long like known. It's specifically gravitational waves. And then last thing is because of that development, that evidence, they were able to start building LIGO. So they're gonna actually focus on detecting gravitational waves because it seems like they're real, and now we're gonna throw a bunch of money at it and see what it does.
Yeah, so what's really exciting about that binary pulsar evidence is that according to general relativity, when two massive objects orbit each other, they actually emit gravitational waves and they lose energy over time. And even though LIGO and these gravitational wave detectors weren't around, they saw that the two stars were spiraling towards each other and their orbital period or their rate of rotation was shrinking. And
Oh.
that rate of decay exactly matched what Einstein's theory was predicting for the energy loss, which means that the energy loss would then be going into gravitational waves. And that was a direct motivation for why we should be building a gravitational wave detector in the first place.
Mm-hmm. Oh, that's why. Okay, that's
Yeah,
very
super
fascinating.
cool stuff. Yeah.
That's so cool. And after let me say this last bit about LIGO. So it started development in the 70s. The original LIGO was built in the 2000 around 2000. And they were trying to detect stuff between 2000 and 2010, and they could not because the instruments were not sensitive enough. So that was just a fact of material science. You could not get the things to work. So they revamped it in about 2010, and then 2015. Maybe I won't steal the thunder, but something special happens then. Hmm.
Mm, that's a really that's a really funky cliffhanger, yeah.
Yeah. All right. Let's go ahead and move on. You
Oh,
tell
I
me
guess
about
the
that.
next slide is mine. Yeah.
Hmm.
I guess, yeah, I guess I wanted to take a brief aside and kind of showcase some examples as to where special relativity sort of came from. I'm seeing a lot of LIGO support in the chat. Agent 9 says LIGO and the Large Hadron Collider are some of the best things we humans have ever built. I'm going to add the James Webb Space Telescope to that. I think LIGO, especially, is a really great example of a large collaboration of scientists coming together. And we'll talk a little bit more about that in the astrophysics portion later on. But yeah, so I just wanted to talk about the
Oh.
Michelson-Morley experiment. This is a really famous experiment. They designed this because at the time there was this idea that there could be an ether that the earth was traveling through, and so they had these two mirrors, one that was parallel to the earth's movement and one that was perpendicular, and if the ether was real, then the speed of light would be different in one direction than the other. But what
Hmm.
they found was that there was no change in the speed of light, and later on this became fleshed out with the postulates of special relativity on the next slide.
Okay.
And one of the key postulates of special relativity is that the speed of light is constant for all observers. The other postulate is that the laws of physics are identical in all inertial frames. And so this is a lot of vocabulary. I would like to pitch myself and say that I do have a series on special relativity on my YouTube channel. So if you want to learn more about this, if this is stuff that excites you, like please go check that out. It's pretty old, but I mean the content is still relevant and accurate. Um, in other words, what this means is that space and time isn't absolute, which, as I mentioned at the start of this lecture, is one of the assumptions that's made by Newtonian physics. Um, and we can solve for these mathematically using the Lorentz transformations. Yeah, the
Woo.
Michelson-Morley experiment is definitely a classic. I'm seeing a lot of love for that in the chat. Yeah, no, it's absolutely great. Um, and it's really cool to see like how we were basically able to think about how objects would behave in relativistic scenarios where objects are approaching the speed of light, something that has never been actually done by humanity. But more importantly, if you go to the next slide, these postulates of special relativity also highlighted some key limits of special relativity. As I mentioned before, this argued for the fact that we need a theory that accounts for both acceleration and gravity, because special relativity only deals with inertial frames, which is a non-accelerating scenario. And the reason why this came about was this famous thought experiment known as the bucket experiment. So if you think about having a bucket and you rotate the bucket, the water starts to like indent inwards. And what Newton was saying was that this rotation would be relative to absolute space, the fixed stars of the universe, and not the bucket itself. But later on,
Oh.
this other dude named Mach, or Mac, I actually don't really know how to
Mac.
pronounce. Is it Mac? I think it's Mac. I realized that I actually suck at pronunciation. A lot of the Orbeez like to call me out on this. Um,
It's okay. I call
and
Minkowski, even though it's Minkowski. That's
it's
funny. That's like that.
Minkowski.
Minkowski with a V. I found that out the other day. But Minkowski sounds hilarious.
I was today years old. Levi Civita, Minkowski,
Hmm.
Mac. Oh my god, my worldview is breaking. I literally cannot pronounce it. Yes, this was the original bucket challenge. But basically, Isaac Newton was arguing that the water is rotating relative to absolute space. And so the curved surface that you'd see in a rotating bucket is evidence of true rotation. But later, Ernst Mach challenged this. Basically, this dude was arguing that maybe the rotation is relative to the mass of the universe. And so what we're thinking about now is that rotation and inertia are actually properties that are tied directly to the structure of space-time. And that sort of started to motivate why we needed to start thinking about gravity as something that interacts with space-time. And if you go to the next slide,
Ooh.
so now we have gravity understood geometrically. And this is where Einstein's equivalence principle comes in. There's a lot of math behind this, but the general gist is that locally gravity and acceleration are indistinguishable. In other words, gravity is a property that's built into space-time. And we see this already, how curved space-time is able to produce observable gravitational effects. And two of these examples is the deflection of light and gravitational redshift. And I guess the more easier example is the deflection of light. When we are looking at stars behind the sun, if you
Mm.
look at this image on the upper right, the star that we see is in a different position than where the actual position of the star is. And that is because the sun's gravity bends space-time so that the light, as the star travels to us, is being bent on its path to Earth. And that is just one of many, many examples of why curved space-time is real and accurate.
That's so cool.
Yeah, no, it's like super cool, like how these ideas like came to be. And so the next thing I wanted to point to is like there's I hand wrote this. I'm sorry my handwriting is not very clean, but I wanted to give a brief aside on Einstein field equations before Aleph, you'll take it away and go a little bit more in depth into this.
Uh,
Um,
yeah.
yeah, so the Einstein field equations basically relate the geometry of space-time, like curvature, to energy and momentum, like the matter energy content. And you can use these equations to solve for things like what does the geometry of space-time look like around a black hole? And that's known as a Schwarzschild metric. Um,
Metric.
so yeah, and then yeah, so Al, if you want to take it away and explore the Einstein tensor.
Yeah. Well, let's see. On my slides, I happen to have just like hid them because I wasn't sure what you wanted to do with them. So I have them. Oh no, that's fine. Okay, I see where you're at. Yeah. So
Okay.
well, you refer to this as the Einstein field equations. Okay, equations plural. What do you mean? Why? Well, it's because of one simple fact. We were talking about tensors and we're talking about indices. We're just keeping track of a lot of things at the same time, right? So, if you take a look, we have um, four special vectors, okay? We have the descriptions of time, and then we have the three spatial dimensions, right? So, time is referred to as a negative and imaginary unit, and then space time is space itself is a real. Okay. So, um, there are 16 possible combinations giving those units. So if we just draw them all out here, we have it looks like 16. But actually, because of some descriptions of the way that the math works, we look at the next colorful version of the matrix.
Mhm.
Uh, so click it. I think
Yes.
through a sec, and so you should see there are similar things going on. So we have G0, G01. So if I just flip the numbers, they're the exact same thing. G01 is the same as G10, which means that following that, we actually have really 10 different descriptions, 10 different equations to keep track of. Um,
So this is because it's a symmetric matrix, right?
yes. So
Yes.
symmetries are important, especially like the I believe this is just a fact of like the tensor calculus, right? And we happen to
Mhm.
be in a symmetric space. So it is pretty cool. There are other studies of other different kinds of spatial calculuses where they do not assume that. Sometimes you even have anti like flipping it makes it negative, flipping it is not possible. Anti-symmetric is what they call it. So we happen to be in one that is symmetric, which is very good for descriptions. However, that means we have 10 different equations at the exact same time going on. Okay? And that is why it is a pain in the butt to really go through all these ones. These are, again, not normal functions. These are differential equations, which means everything is related to each other in some capacity, and it is a pain in the butt. That's why we make supercomputers do these things. Um, but the assumption with Einstein, he had discovered by making the description a lot simpler. So imagine if you were talking about instead of saying like sines and cosines and stuff like that, you just said like ones and twos and threes. That's basically what he did. Made it a lot simpler, and then that's how we were able to discover some stuff. However, because of that simple description, by simplifying it, he did not want to assume that because he simplified it that it was right. That is why he was super skeptical about it.
Mm. Wait, I love this visualization of what's going on here. There was a question in the chat about, I think you partially answered this, but somebody asked, Sonoda says, is symmetry of G due to some sort of physical symmetry, like the isotropy of the universe? I did want to say that I do know that the homogeneity and the isotropy of the universe do affect our understanding of these different symmetries. But I'm also curious, like, is this a direct effect on the Einstein tensor in particular?
I do not think this is a special case. I think it is just a description of space-time. So that is why
Mm.
Minkowski it is described as the same thing. So it goes it's a lot simpler than it is. It really is just like a matter of fact. Not to not to like not hype it up, but I'm just saying that the descriptions that we have were already realized, and it just happens to be something that is simple to describe.
Yeah. I think Sonoda, one thing, if you want to look more into this, the symmetry that I've been thinking about, this is a more astrophysics aspect. There's something known as the FRW matrix. It stands for like Friedman, Robertson, metric. I'm forgetting like the last names, but if you just look up FRW metric, it's the first thing that comes up. Um, and when you're solving the Einstein field equations for the universe, you can use the symmetries of the universe into this FRW metric. And specifically, you're using two symmetries. You're using homogeneity, which is this idea that there's no preferred location in the universe. Basically, it's like the same at every point, roughly. And the isotropy of the universe, which means that in any direction you look, the universe looks roughly the same. So that means that there's no preferred direction. So if you want to take a look and try to learn more about the symmetries and how they affect cosmology equations, I highly recommend that. There's a really great Wikipedia article on this.
I also want to point out real quick. This
Mhm.
is described as the Einstein tensor. It really is a description of other tensors, existing tensors. So, so if you look at that first R mu nu bit, that is actually just the Ricci curvature tensor by Ricci, when he was doing Riemannian calculus and stuff. And then the minus
Oh,
1/2 R G mu nu. G mu nu is the metric tensor, and R itself is the curvature scalar. So, uh, Einstein just put it together and slapped his name on it. I'm sorry. I
that's so funny to me. Like that.
it's just combining things together. I'm telling you, it is so interesting that it's fun. It's fun. It's fine. Let Einstein have it. He died a long time ago. We're happy. We're celebrated, and now we have LIGO. Okay, let it be the case.
If somebody's like gives me a free opportunity to name something, like I'm taking it.
Everyone wants it, but Einstein really got like he lives on. Like he is the name
Yeah.
of a smart person. Einstein. Like okay. Did he really need everything though? I don't know. That's what I like talking smack about.
What's
I
really
apologize.
crazy to me is that people think that he won the Nobel Prize for equals MC squared, but he actually won the Nobel Prize for the photoelectric effect, which is equally as valuable and interesting. Um, so yeah, no, I mean, obviously, like he definitely deserves a lot of credit for sure.
What
Um,
if you could tell me because I don't know. What is the photoelectric effect? What was that again?
oh, so basically, the photoelectric effect was this. He basically did this like idea, this experiment where if you shine light on a metal surface, he found that if you shine light with high enough frequency, high enough energy, then electrons are ejected. Um, and so
Oh.
basically he like was able to I feel like I'm not doing a good job of explaining this.
Mm,
He was able to show that like light is able to behave like particles um
that's
in
what that is.
photons. Yeah. Um, but more importantly, it also was able to lead to wave particle duality, which then became the basis for the entirety of quantum mechanics. And we use the photoelectric effect for a lot of things nowadays. Yeah, like Lena in chat just says, we use it for solar cells. Yeah, we use it for solar cells, we use it for photodetectors. The way that we take images of space on CCD chips is that we collect electrons as photons hit this metal surface. And from counting those electrons, we're able to determine like what the brightness of an object is. Um, so yeah,
So fascinating.
I know it's super, super cool stuff.
I do see a chat from 𝖘𝖔𝖈𝖎𝖊𝖕𝖎𝖙. Was Einstein just in the right place at the right time? Yes. Well, putting it together, I'm not discrediting like a lot of things. Clearly, he got a Nobel Prize, right? So these are like the brightest minds in science, right? So I will not discredit the fact that they did a bunch of cool things. Now I will laugh about the fact that people keep emphasizing that he did it. No, he was a theoretical physicist. He put the things together. He was not the mathematician that proved that some things are in fact true. He just put them together. And honestly, I think that needs to be recognized a lot more because in mathematics, yes, we do the groundwork for lots of theory, and later on, just somebody happens to be able to make it useful, and that's cool, and we like that. But the person that made it useful usually gets all the credit, and at least we put the name on the things that were put it together. Except Einstein put the whole thing and he called it his own tensor and why, whatever. Or maybe it's just, I wonder if it came after the fact, you know? I wonder if people refer to it as the Einstein tensor, not Einstein calling himself that.
Well, I think Einstein also like it wasn't. I think the right time was. I think like he was able to spark it being the right time. I'm gonna send this Wikipedia thing in the chat. It's a link to a book. It's by Benjamin Labatut. He writes absolutely amazing stuff. If you want to learn more about the history of really crazy discoveries, The Maniac is a really good book. He wrote another really famous one. I'm blanking on what it's called right now. If someone in chat knows, let me know. Um, but at the time, like when Einstein was around, there was really this boom in like trying to understand quantum mechanics, trying to really piece together these domains of the universe that we have never considered before, like really fast travel with relativity, with the smallest particles with quantum mechanics. And I think at that time there was just so much interest, and that's how we got a lot of people working on these really cool ideas at the time. And so if you want to learn more, I really recommend this book. It really goes into science history if that is something that you're interested in.
That's so cool.
Yeah.
And I see one other thing. Someone mentioning, I think Gauss mentioned Gaussian. He says that same thing happened with Maxwell's equations. Maxwell only worked on one of them. What? Is that
Oh,
true?
yeah, I think I heard about this. Yeah.
Did anybody actually do anything? Huh?
Well, to well, to be fair, I mean, I wasn't Maxwell the one that like brought all four equations together though, because I think that was like the big contribution.
Yeah, no, I think that is the case. I just
Yeah.
find it to be really funny because yeah, honestly. And then by the way, this description of gravitational waves is the gravity equivalent of those Maxwell equations, isn't it?
The description. Oh, I'm not sure. What do you mean?
The differential equations, I believe. Yeah, I mean in that regard. Because that's what I've heard of the gravitational waves as that description. I had heard of it as it is the gravity equivalent of electromagnetic waves.
Oh,
So,
yeah. I mean, yeah. I've heard about this. Yeah, Maxwell's equations is sort of analogous. Yeah, they're both field equations. They both have tensors. Um Yeah, if you ever take like an ENM course, I don't know if there's any like physics students in the chat, but it's really cool to see these like parallels across the universe from ENM to gravity and relativity. Yeah, Maxwell's equations implicitly contain special relativity. Well, there's this one
ooh.
concept that's taught in classes that I feel like is kind of misleading, but it's this idea that like if you are moving in a different frame of reference, electric like current becomes like magnetism. That's not quite true, but it does come to show that the Maxwell equations do implicitly contain special relativity and they are implicitly connected.
So cool. I
Yeah.
like putting these together. I'm talking too much on my side. Let's go ahead and move on then. Okay.
Oh yeah, I mean no worries. I mean this is super cool stuff. Okay, so the next part is the astrophysics section. Um, so let me make my slide a little bit bigger. So I just wanted to share about the astrophysics of gravitational waves. Oh my God, wait. I'm so glad that you included this in the presentation. So Aleph made this super cool animation. I would love to post this on YouTube, like as like like a collaborative like short or something. It's like two black holes colliding, and it just looks absolutely chaotic. Um,
I whipped that up. And there's a few like I'm not satisfied because I know technically it's not the best visualization, but it looks pretty cool, doesn't
I
it?
mean, it looks great. I mean, it looks really, really cool. Yeah, everybody go clap for Aleph's amazing blender skills in the chat. Um, Yeah, so I guess like why black holes? And so the thing is, in order for us to detect gravitational waves, we need obviously the gravitational waves to be detect like to be big enough for us to hear them.
Hmm.
And that only happens for very extreme events, like when two black holes collide. And so if you go to the next slide, I just wanted to post a map of different gravitational wave observatories. I think this one's a little bit outdated, but um, as you can see, finding gravitational waves is a worldwide endeavor. Um,
Ooh.
Many of you guys may have already heard of LIGO. There's also Virgo, which is right here, and CAGRA, which was finished in 2019. And all the combination of these altogether has detected over 290 gravitational waves over 4 observing runs. And some of this data has already been released to the public. And
Ooh.
so with all of these events, we've been able to piece together like a really great view of what do black hole populations look like in our universe.
Hmm.
And so the ones that you may be familiar is the one in Hanford, Washington, and the one in Livingston, Louisiana, which are which are currently operating. And there's also Kagura in Japan and the Virgo detector in Italy. And there are definitely more observatories that are being planned, and we'll talk about that at the very end. And having these observatories will help us basically triangulate the locations of these gravitational wave events.
So cool.
And so on the next slide, I actually
Wait.
wanted to.
I want
Mhm.
to want to mention one thing real quick. So first off, I do want to contribute that I actually the whole reason that this discussion happened in the first place is because I have happened to just be around one of these observatories, right? And I want to ask you, if did you by chance go to any one? And I want to know which one.
Oh, I did briefly, very briefly swing by the Hanford one.
Mm,
Um, but
I was
I
there too.
didn't actually like briefly as in like I didn't even go to see it. I was just meeting somebody who works there. But you
No.
actually went to one, is that correct?
I went to the Hanford one, which was
Oh,
fun
no
because
way.
it was okay. Only bothered me is that I was doing an internship at the time, and so when I was stuck out there in Hanford, Washington, I was expecting a very different climate and landscape, and then I got the exact same thing I have at home, and I was very disappointed. But even worse was that specifically Hanford is very hot. You know, it's in the desert compared to Livingston, Louisiana, where they put it around a bunch of beautiful trees and stuff. No, put it in the middle of the desert because the government happens to have ownership over there, and nothing's gonna be out there because you know what? The reason why Hanford's on the site is because of the Manhattan Project, right? So a bunch of the soil's irradiated. They can't play around with it. So the government said, "Hey, let's go ahead and start. You guys can play over here. Sure, why not? Fine." So that's where I was at. I had fun. It was cool.
Wait, that's crazy because I've been to Seattle a few times and I just feel like the Seattle weather in the summer is like very like temperate and refreshing.
Yeah, it is, isn't it? It would have been cool to go.
Well, I do recommend Seattle is definitely a cool place to be as well. They have a lot of stuff for SpaceX over there and Blue Origin and a lot of really exciting aerospace work. Um, but yeah, no, I think it's really cool that you actually got to visit the site. Like, did you get a tour and everything
Mhm.
or?
Yeah, I got to see. We got to tour the outside. And I'm pretty sure we're gonna talk about the material science of how this thing works, right? So, I won't spoil too much, but like the way that it is, we're outside, and it's of course in the middle of the desert in the summertime. So it was like, sorry, I'm American, but I'm gonna say it was like over like 110 degrees Fahrenheit outside, which is pretty
There's no,
freaking hot.
wow, that's crazy.
Yeah, it was great. And then we went inside with the AC, and then we saw all the graduate students crying about, it's so boring out here, but it's pretty cool. I'm like, nice. So,
Wait, that's so cool. I'm wondering, has anyone else in chat visited a LIGO or any other gravitational wave observatory? And if so, how was your experience? Yeah, I was gonna say, like, it's kind of probably, I mean, the arms are like what? Like, isn't it like a few miles long
yeah, I think
on each
they're about,
side? Yeah.
yeah, a few miles long, perpendicular to each other, or
Yeah.
orthogonal, or
Yes.
normal. Sorry. Um,
Or yeah, orthogonal. Yeah.
what do you also, what does LIGO even stand for? Let us talk about that just for a sec.
The LIGO stands for long.
Mm,
Wait,
I
that's
got it.
actually. Wait, I was gonna Google this real quick. Laser
Laser
interferometer.
Interferometer Gravitational Wave Observatory. At least
I
in the States and India. So
Why did I immediately think long something something? I knew the I stand for interferometer, but
yeah, so what do those terms mean? Let's break that down because of course like laser, there's a laser going on, right? And we have these cool little things. And then interferometer, which means something we're detecting when waves interact. Gravitational wave, that's what it's for, and then it's an observatory to look at it. And why are there so many?
yeah. Yeah, I mean, the reason why there's so many is because each of these can basically detect a gravitational wave, but in order for us to figure out where the signal comes from, we need a lot of them scattered around Earth. So, like, let's say that you are, I don't know, trying to listen to a sound, right? And you're just like standing somewhere and it's just you. and you hear the sound, right? And then you kind of don't really know where it comes from. But let's say that you had a whole grid of people listening, and they're like, "Oh, I heard it from over there," and somebody else is like, "Oh, I heard it from over there," and they're able to piece together where did the sound come from. And in a similar way, having more detectors means that we're able to figure out where exactly these black hole events or gravitational wave events come from.
Oh, it's like trigonalizing it then, huh?
Yeah, it's like triangulation. Yeah, exactly.
Oh, I thought it was for coincidence data. You want to make sure that they're all. Well, okay, hold on. Let's go ahead and move on to the next slide. I think if
That's
you're ready.
also a factor too.
Yeah.
Yeah, so that's also a factor too. These detectors have to be incredibly sensitive.
So,
A gravitational wave that's like passing through Earth is an incredibly small, like leads to an incredibly small distortion in space-time. Like, let me see, let me actually Google real quick how big that distortion is.
uh,
Yeah, I was gonna say it was.
I
Yeah,
believe
gravitational
it's.
waves passing through Earth are about 4 atometers, or about 1/1000th of the diameter of a proton. Like, and so if you have one detector detect that, I mean, that could be anything, right? Like if a truck passes by, I mean, that vibration is probably more than 4 atometers, right? And so having all these detectors means that we can really confirm whether an event takes place.
That makes more sense. So you gotta make sure
Yeah.
everyone's on the same page so that we can reference each other's homework. Yeah, okay, that makes sense.
Yeah. And somebody asked, like, attosecond, yes, if I recall correctly, the sensors need attosecond precision. So one might wonder, what is an attosecond? How small is an attosecond? And so one really great analogy for attoseconds is think about the ratio of your heartbeat to the entire age of the universe, 13.8 billion years.
Oh,
That is the same ratio as an attosecond to your heartbeat. So this is
wow.
a really, 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 really sensitive instrument. Isn't that crazy?
That is a crazy scale.
Yeah, it's incredible to
What?
me that we're able to detect something on that scale.
That's amazing.
Yeah, it's too tiny. Yeah, no, it's very tiny indeed. Okay, so we could go to the next slide. I
Hmm.
wanted to briefly highlight a really super exciting gravitational wave event. This was making its way around the community, and I mean, a lot of gravitational waves do in astrophysics, but this one in particular was interesting because this is the most massive black hole merger that was detected at the time. I don't know if it's been updated since then, but um, this paper was, no pun intended, made waves in the community.
Ha. 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 Sorry.
I'm so sorry. This is such a cringe pun. Lol. See, we have appreciation in the chat. Oh, and if you go to the next slide, I just wanted to show you, if you load up this paper,
Whoa.
the authors list is like 7 pages long. So the first 4 pages that I've screenshotted here, those are all names. And then there's everybody's affiliations afterwards. Um, it is actually unbelievable how large these collaborations are and how many people from all these different nations are coming together to figure out if we could hear black holes merge in the universe. And so I just wanted to highlight how incredible these collaborations are.
So cool.
Yeah, everyone's shocked. I know. Isn't this so surprising? I like opened the PDF and I was like, wow, this is a pretty long paper. And I was like scrolling down and I just could not find the ending to this paper. This is a huge collaboration.
Someone said they included the LIGO janitor. Yeah, everybody's involved. they'll they'll
Honestly,
think
everybody's involved.
they'll
Yeah.
think the
I
ants that
wonder
were
what the
around
record
it
is.
because they're interrupting
Yeah.
the instruments.
Yeah, no, I mean, it's incredible. I feel like I haven't seen, I think the Large Hadron Collider might be a little bit larger, but I mean, I've never seen it like listed out like this in a pretty long while. Usually they just say the LIGO collaboration or the LHC collaboration for the Large Hadron Collider. Um, so yeah, if you go to the next slide, um, I will be taking some time to explain this really cool event. But if you want to read more on it, there was a recently published astrobyte on this event, and I'll be taking some snippets from that as well. So if you want to learn more, there you go. Um,
Very cool.
All right, so if you go to the next slide, GW231123, a signal detected in November 2023 with a measured primary, which is the larger black hole, has a mass of 137 solar masses, and a measured secondary, or the smaller black hole, mass of 101 solar masses. This makes gravitational wave 231123 the largest mass gravitational wave event to date. In other words, what this means is that we have one black hole with 137 solar masses, a smaller black hole with 101 solar masses, coming together, rotating around, rippling space-time, and then coming together in this giant gravitational wave event. And that is what we detected.
That is pretty big stuff. Wow.
I mean, yeah, it's absolutely incredible. These are monster black holes. And so if you go to the next slide, what's
may I ask
yeah?
real quick though? So the only reason why we can barely even detect them is because of it's just because they're so far away, right? Like if we were like right next to them, like well, they are like really big events when they happen, like right there, aren't they?
Yes. I mean, we would probably not want to be very, it would not be ideal if we were near a black hole
Ah,
pair as they collided. That would lead to some potentially negative effects. But yeah, no, these gravitational waves are traveling throughout time, through space over light years, and
mm-hmm.
they reach us.
Barely.
Yeah, that's amazing. Yeah, no, it's
Yeah.
incredible.
So if we were closer, I mean, I just might want to ask then, if we were closer to like one of these celestial events, would it be easier to detect them?
I mean, of course, yes. I mean,
Hmm.
if we were closer to a gravitational wave event, we would be also able to detect different types of energy being released. Um, a lot of radiation, of course. But also, yeah, the gravitational wave event would definitely be much stronger. It would not be a very pleasant experience, that is for sure.
Oh, I see. Okay, very cool. All
So
right, very
somebody
cool.
asked in the chat, Agent asks, with the amount of energy that spews out through gravitational waves, does the mass of the resulting combined black hole not equal the sum of the two masses?
Oh
That
yeah.
is exactly the point.
Mm-mm.
Um, that is one of the theories that was provided when we were thinking about gravitational waves. And that's exactly what we see in these papers. When these black hole events merge, the total mass is less than the combination of the two.
They spew out so much energy that it's just gone.
Yeah. I guess somebody in the chat says that it would be technically harder to measure the gravitational waves if we were closer to the black hole event because technically we would all be dead. Um, so
Okay, yeah.
yeah, technically we would be dead. And thank you, Val, for joining the chat.
Brilliant.
Yeah, so I guess if you go to the next slide, what's more interesting is that the signal has high spin. What that means is that the black holes, when they were before they were merging, were spinning really quickly. Um, And so you have this dimensionless spin constant, with one of them being 0.9 and one of them being 0.8, and that's really intense. Because typically, I think a black hole spin is around like what, like point 3 to point 0.5. Um,
Does that mean one is like spinning
one
around
is
the
like
speed of light?
super fast. Yeah. Let me
Uh,
see if I can I'm gonna quickly look up the dimensionless spin. Yeah, no, there's like a pretty complex equation. It has to do with like the angular momentum and the mass of the black hole.
uh,
But yes, uh, a spin of one would mean that it's spinning really
the
fast.
speed of light, if
Um,
you will, right? Like literally.
yes, that is basically the extreme Kerr case is what it looks like. Yeah,
Okay.
you probably are more familiar with this than I am.
I
It
only
basically
put it
means,
together. Sorry,
uh-huh.
I only put it together because like I'm from a scale from decimals and to like a one. Like, what's the fastest you can possibly be? One. So probably like the fastest angular momentum would be is like as close to possible to like the speed of light. That would make sense. Probably. I guess that was a point nine sounds pretty cool. It just reminds me of those Lorentz transformations, the Lorentz factors. So yeah, you're pretty
Yeah,
close, but kind of not relativistic actually.
yeah, it's a dimensionless spin constant. So when you're at one, what that means is that the black hole is spinning so fast that the space-time around it actually gets twisted around the black hole. And I actually
Oh.
talk more about this in my special relativity series, why rotating black holes are so weird. In fact, they're so weird that actually inside of a rotating black hole, space and time get like flipped. I could go off on a tangent about this, but it's super cool stuff.
I see. Okay, that makes way more sense to me. Okay.
Yeah. And so this black hole duo is interesting not only because it's super massive, but also because the black holes themselves have really high spin. And that actually poses a challenge to scientists. And we'll get into that in just a second, but on the next slide, you'll see what the signal actually looks like. This is also known as a chirp, and if you go online, you can also hear sonifications of this. It kind of just sounds like a like boop, like a really like sharp upturn in sound. I'm trying my best to mimic this, but I think my sick voice unfortunately is unable to do it. Um
I don't
wait, you did it too. Yeah. Boop.
know.
Um yeah.
If
I
that's
think
right.
there's a YouTube video online that actually like shows the two black holes merging with the sound in the background. Super cool.
Oh,
And
okay.
so they detected this at the Hanford location and the Livingston location. Oh, I guess I included this. I think we can skip this next slide, but this was an infographic that they made, uh, showing how exciting people are about this event, about it being the most massive binary black hole observed to date. Um, all right, so if you go to the next slide, I mentioned earlier that the spins of the black hole poses a challenge, and you might be wondering, why is that a challenge? Isn't it super exciting that we're seeing an event with big spin? The issue,
Mm.
though, is that this event is so special that we know basically nothing about how black holes merge when the spins are really high.
Oh.
And the reason why this is a challenge is because in order for us to determine the mass of the black hole, the properties of the black holes, we need to use something known as numerical relativity. That's basically like using simulations in order to extract the properties of the black holes. In order to do this, the scientists use Einstein's theory of general relativity to develop the models to try to model the black hole event and try to recover its properties. But these are like really complicated systems with a lot of parameters, and Einstein's equations, as we've seen earlier, are like pretty darn hard to solve. Um, so in typical signals, what we get is that we are able to, our models are so strong that we're able to figure out what's going on. But for this event in particular, the scientists found that there was a lot of disagreement in what the spins of these black holes would look like. And so what the plot here shows is on the x-axis, this is the spin of the first black hole, and on the y-axis is the spin of the second black hole. And this purple model shows the purple line shows what the model gave us when we were able to compare 5 different models. And as you can see, the distribution is very, very, very large. But overall, they concluded that the spins would be pretty high, as you can see with the peak being at 0.9 and roughly 0.9 for this one. And so the challenge comes from the fact that although our models do predict spins of higher than 0.8 for each black hole, this is a region where unfortunately none of our models are really properly calibrated. And so we do need to have a better understanding of black holes in this very interesting range. And so if you go to the next slide, you may now be wondering, why is this event so exciting? And so one of the things that LIGO and these gravitational wave collaborations are trying to figure out is that they're trying to figure out at what range of masses can black holes form. And typically, we see a lot of black holes in these ranges and later on here. This occurs when stars die, and really massive stars die, and they collapse in on themselves and they form black holes. We also have yeah, so we have kind of 2 areas here, but there is this mass gap where we have historically been unable to find a lot of black holes. And this is roughly 60 to 130 solar masses. And so the question is, why are we seeing a lot of black holes here and a lot of black holes here and really nothing in between?
Mm.
And that's one of the questions that's being posed by this collaboration. And so if you go to the next slide, one of the current theories as to why this would take place is this idea known as a pair instability supernova. And what this means is that we're basically getting a lot of free electrons and positrons being formed in the collision between atomic nuclei and energetic gamma rays. And that temporarily reduces the pressure of the star that's trying to support itself. So inside a star, there's like always a battle going on between pressure and gravity. And once gravity wins, the star collapses in on itself. But inside of these really massive stars, sometimes these electrons and positrons can form, which then reduces the internal pressure, and that creates like a mini explosion.
Oh.
And so there's a lot of theories as to what's going on with this mass gap and why and how could black holes potentially form inside this mass gap. And I just wanted to point towards this right side here. It's known as hierarchical merging. And it's this idea that black holes form by merging with smaller black holes and becoming even bigger black holes. And maybe in this way we can get black holes that are sort of within that mass gap. And so with that, that's the reason why this discovery is so exciting, because these black holes are just on the edge of this mass gap, which can then help us understand why do we have this mass gap in the first place and what can we do to fill it. So I guess I wanted to show the actual plot, if you're interested here, about numerical relativity. And this is similar to the previous plot where on the x-axis we have the mass of the first black hole, and on the y-axis we have the mass of the second black hole. And what we see is that the primary mass is more massive from the expected and previous signals, and that either black hole, as indicated in this yellowish region, would be in the mass gap here. And this is just super exciting. We're still doing a lot of active research on trying to understand how do black holes evolve over time. And now with the emergence of new telescopes, we've been finding black holes to be a lot larger in the early universe than we anticipated. So understanding how these black holes come together and how they evolve will give us a better sense of how did these black holes come together and why are they so big in the early universe. So I know I've been yapping for a pretty long time. This is super exciting stuff. And again, I wanted to point again to the Astrobyte if you want to learn more about this discovery and others in a more accessible format.
Pretty cool. Someone asked in chat, why isn't this diagram symmetric? What is this about?
Yeah, so using our numerical relativity models, you can actually sort of determine from the chirp signal that you saw earlier about whether one black hole will be more massive than the other. And if you typically imagine a black hole collision, it wouldn't be the case that both of the masses of the black holes are the same. So the symmetric diagram would mean that both of the masses of the black holes are the same. Instead, what we're seeing here is that there is a primary mass and a secondary mass. And this is an estimate of what those masses would be. So I hope that answers your question, Doc Rect.
Okay.
Yeah.
This
So
Sorry.
I just wanted to quickly point to some resources. LIGO is great. They provide a lot of resources if you want to learn more. So if you want to get notified about when a gravitational wave event is detected, they have both apps that you can get on Apple and Android, as well as websites where you can actually see. If you go to Astro Colibri, it's super cool. Like, you can see like what the event was, what it was, and it's just it's a super cool way to like interact with the science that's going on here. And if you go to the next slide, if you want to read more, LIGO also publishes these science summaries. It's basically astrobytes, so explaining things in a way that is familiar for a general lay audience, but for gravitational wave nerds. And they basically break down the papers and they break down the figures and they explain what they're discovering. And they do a pretty good job of posting really consistently, so you can read about their latest discoveries there. And finally, if you want your kids, I don't know if there's any kids in the chat, but if you want your kids to learn more, LIGO actually published an ABC book. I just wanted to show this. It was like B is for binary black holes, T is for travel time. Like they actually have this like kids book posted. It's absolutely hilarious.
It's like those elementary, kids first elementary, um, really complicated subject books. I've really liked them.
Wait, I found one the other day that was like quantum mechanics for babies. And I was
Oh,
like,
I know that
I
one.
don't think that's a good way to start a child's life, but okay.
Like that, I think they're more ironic than they are like useful.
Yeah.
I
I think it's more for adults.
Yeah, exactly. It's like, okay, let's learn our elementary calculus functions or something like that, you know? It's like, what?
I would love to have that book. Yeah, no. Wait, someone says I know what to give my friend's baby. One
Absurd.
of my profs would bring his 6-year-old daughters to guest weekly lectures. Oh, I used to have a professor who'd like bring their kid into lecture as well. It was a lot of fun. It was very adorable. It's actually not too scary, huh? So maybe it is a good gift. Maybe this is a good gift idea for the folks in the chat.
Is it? I'm not gonna lie, I kind of like prepped a lot for this week. I was like, I am way out of my league learning this stuff. And then now the babies are learning it? What? That is cool
Well,
though.
it's very funny.
That's really cool.
All right, let's see what's on the next slide. Oh,
Mm. Oh
well,
yeah.
I just wanted to quickly skim over this and just showcase Catalina. Let me actually put the Discord because I know we have a few new people in chat. Um, there is a Galaxy Discord, so please feel free to join. Catalina posted, I don't know why my model's glitching out, by the way.
Mm.
Catalina posted some back of the envelope calculations done for merging black holes. And although there's like a lot of assumptions made here, like using Newtonian physics and so forth, um, I think it really comes to show that you can really play around with these ideas and play around with these equations yourself. And I think Catalina, from these basic back of the envelope calculations, was able to estimate roughly by an order of magnitude the masses that were measured by the LIGO collaboration. I don't know, have you ever taken a back of the envelope physics class, Aleph?
In what regard? What do you mean?
There's like back of the envelope physics. It's kind of like order of magnitude physics. You're basically doing physics, but you're making like a lot of general assumptions and like um doing some very quick calculations and just getting a sense of like general like physics concepts. Like for instance, like the most famous back of the envelope physics question is like how many piano tuners are there in the city of Chicago?
Oh, I see what you're saying.
Yeah.
I am more axiomatic, so I do like when my definitions are nice and fun. I'm not really good with estimates, nor necessarily do I much care. Uh, you know,
Oh no.
it's just my taste. I like proofs. I like the rigor. So I'm a lot more particular with stuff like that. But I do like when you can generalize a lot of things. It is pretty cool when you can like say, plus or minus 6 or 7. Yeah, okay, sure. I'm down with that.
6, 7.
6, 7.
Oh
So
my God. Of course we wouldn't have a stream without 6, 7.
of course, um, really fun.
Yeah, these are also called Fermi questions. Uh, uh, Aleph, how could you? I mean, if anybody,
Axioms can
I
only
think
get you so far. The only
Mhm.
axiomatically consistent quantum field theory is one with no interactions. Well, guess what? You might not believe me when I say that I am not an experimental physicist. I could care. You guys play with it. I'm okay with it. I respect what you guys do.
Yeah. Aleph, so you do more math things as I mean, I guess you're a math VTuber.
Yeah. Oh,
So,
and let me share off that my Discord as well, because I also want to plug myself in. Yeah, I should have it in there
oh
as
yes, yes,
well.
yes, please be sure to send that in.
Yeah, I cover mostly math topics, and I want to try to do some animation stuff and maybe video essays at some point. But real life, is hard, and like just like getting you on the same wavelength, if you will. It is hard to like organize some things. So any more help would be fantastic. So, um,
Yes. I mean, obviously, like, I'd be happy to help out with anything that you're working on, and it's super cool to see, like, I mean, I guess we were messaging, but like pre-debut as well, so it's super cool to see like how your channel has grown and what you've been, interested in.
Oh yeah.
Agent 9 says, Senko taught me how to estimate how much time it will take for a lens to burn something. I do love Dr. Stone. I was actually thinking about this last night. I would love to do a series where I teach back of the envelope physics. This could potentially be like a video series for my long hiatus that's coming up in like half a year. Um, and so I think something like that would be super, super cool. So if you're interested in that, please let me know in chat. Or if that sounds boring and miserable, please let me know as well.
Mm.
But I think back of the envelope physics is a really nice skill to have. Um,
Maybe I should catch you doing one of those at some point because I need to learn the process. You know, it'd be really cool to be like, oh yeah, this or that. Oh, this theory already exists. Just use this.
yeah, yeah. I mean, I think like one of the things that I really see often in physics students is that like with especially with AI nowadays, it's just so easy to feel like you're just plugging and chugging or just deriving things that don't really have any physical beating.
Hmm.
Um, but with back of the envelope physics, I was thinking, oh, thank you, Audit, for following. Um, sorry, I just totally lost my train of thought. Oh, I was saying that I think it's really nice to actually get a physical intuition for things and to understand like what does the viscosity of a liquid really mean? Like, from the viscosity, can we determine whether a
Oh,
liquid is viscous or if it's turbulent?
oh,
And for instance, like one of the things you can measure is like the speed of blood in an artery, and you find that it's in the laminar flow regime, and that makes sense because obviously we wouldn't want turbulent flow in our bloodstream, right? And so like getting those kinds of intuitions would be really, really interesting to share.
I think I have the next collab stream then. Okay. So not only was
Ooh.
out there in Washington, but I was also out in New Zealand doing plasma simulation research. So the math makes a lot of sense. Navier-Stokes makes sense. Electromagnetic electrohydrodynamics. It was really cool. All that for plasma thrusters. So oh, it's so cool. So if you said something about laminar flow and viscosity, I'm like down with that.
Yeah, wait, that would be so cool. I mean, if you did plasma physics stuff, have you ever thought about like were you ever doing like more fusion physics things like at the tokamak? And also feel free like to pass on any questions if you don't feel comfortable answering.
I was only in New Zealand. Basically what I was
Okay,
doing
cool.
was I was supposed to start implementing a simulator for small scale plasma simulations. So
Uh-huh.
turbulence is where you consider the mass of the electron. Of course, with plasmas you got a bunch of like particles and magnets flying around, which means that it
Hmm.
induces an electromagnetic field, which means that it affects the next time step, right? So they all start affecting each other in some capacity, but usually for the simulations, you assume the electron is not there because it's so massless. It's a 9.11 times 10 to the minus 31. That is kind of small.
Uh-huh.
So
Yeah.
but for small scale turbulences, they probably do matter, and that affects us probably maybe not necessarily in the quantum scale, but like in some sort of small capacity. We're not talking about like galaxy sized things. We're talking about like the about an inch, if that, on a plasma thruster, which is important for research, right? Why not? So that's what I was
Yeah,
doing.
exactly.
So I would be running those simulations. I learned what a Reynolds number is. I loved it actually. It's super cool. It's
Wait, we should
generating
totally do
data.
a stream on this. That's so cool.
Yeah, it's so cool. So generating data, different from using real data, right? It goes to show. So I loved running the simulations for about 10 hours at a time, and then it'd crash, and nothing got saved.
Oh no.
And that was the entire experience. It was so fun.
Well, I would love to do also, I mean, I have to admit that fusion physics, plasma physics is not my area of expertise, but I'd love to learn more and also talk more about like back of the envelope stuff for like laminar flow and that kind of stuff. I
Mm.
did visit the tokamak down in San Diego. I think there should be a YouTube video, YouTube VOD where I actually talked about this trip and I was able to meet some scientists there. I have to be so for real. It was definitely not my area of expertise, but it'd be super cool to talk and, learn more about it together.
That'd be really cool. Oh, I shoot.
Yeah.
That's really close to me. I could probably actually just go there myself. Shoot. Man, there's so many things in specifically California. There's the JPL National Laboratory, and
Oh,
then
have you visited?
I applied and they rejected me.
Oh, oh no.
But
Well, NASA Jet Propulsion Laboratory is absolutely amazing. I've visited there many, many times actually, and I guess this was probably before your time, but I actually hosted a fundraiser after a lot of people in that area were displaced by the LA wildfires last
mm,
year. Hmm.
oh, I remember those.
Yeah. Wait, JPL is absolutely amazing. I would if you know any scientists there, like I would highly recommend going on a tour. It's
Uh,
the kind of place that, you know, you go to the cafeteria and there's like somebody working on the next Mars rover, there's somebody working on snake robots in Enceladus, there's somebody working on a spacecraft going to the sun, and there's somebody working on understanding galaxies. Like it's just such an incredible, vibrant academic place.
some of my colleagues from New Zealand actually went and interned over there at JPL. So while they're out here, I got to hang out with them. It was really, really cool.
Wait, that's so cool.
So yeah, I mean, I'm telling you, this stuff is so close to me. I can just go and do things if I wanted to. Shouldn't I? Again, I'm not an experimental physicist, so I don't necessarily need to go to these observatories. I kind of just want to write on a whiteboard all day, but I don't know anything else, and I kind of like touring around. So that'd be cool. That'd be cool. I gotta go there at some point.
Yeah, I mean, if you ever need any recommendations, I got you for sure, especially when it comes to the NASA Jet Propulsion Laboratory. So.
Hmm. It's so big.
Cool.
Yeah.
Well, I was looking at the rest of the slides. We do have some questions left, and I know we're kind of up on time. So I think we could do some like rapid fire. So we did get some questions from you all. I think maybe we can spend like at most like a minute on each. And I think a lot of these were kind of astrophysics oriented. And we'll try my best to
Yeah.
answer. And again, if you do have questions, feel free to send them in the Discord. And we'll see if we can get to them on there as well.
Hmm.
All right, so so the first question that we got was, do we have any hope of measuring the memory effect? What would the detection scenario look like? And so quickly, I just wanted to explain what that is. So if you look at this GIF here, after this gravitational wave event, you can see that the orientation of the dots has been slightly altered permanently. Basically, what this means is that the position of masses in space get damaged or like kind of like permanently altered by a gravitational wave. And the detection of these events has been suggested as a way of further validating general relativity. However, as you can imagine, a gravitational wave event is on an incredibly small scale. As we were talking about, it's attoseconds and attometers. I think we're kind of far out from measuring something like this, but I think it's a really cool concept to think about. I don't know, Al, if you want to add more on that.
I can't.
Oh, well, I just wanted to sort of show this really, really cool effect,
That's a
but
cool picture.
yeah.
So you're saying that things get permanently like displaced because of the waves?
Yeah, so it's like if a gravitational wave, like if you think about like I don't know if this is a good analogy, but like let's say like a wave passes through a beach, right? And then the sand gets like displaced and it's like kind of
Oh.
just like permanently moved.
Mhm.
It's kind of like that, but in our universe. And there's been these ideas that you could actually measure these little displacements in the universe to sort of hear the echoes of these gravitational waves.
That's cool. And I'm guessing you could probably do some geometry backwards to find out what the initial shape is.
Yeah, I mean, it could be cool to like extrapolate like what kind of event took place that led to this distortion in the first place. But detecting gravitational waves in and of itself is already such a huge challenge that I think we're a little bit far out from measuring this memory effect, but is definitely very interesting to think about.
Very cool.
Um, yeah, so the next question that we got is favorite next gen gravitational wave observatory. I don't know. Do you have an answer, Aleph?
Specifically gravitational wave. I think they're cool, but they're actually not my favorite kind of wave or favorite kind of particle observatory. I really like neutrinos. I'm not gonna lie. Neutrinos are pretty cool.
Ooh. Do you have
Um,
one in mind?
there's that one I think like miles deep in Japan or something, right? I think
Yeah.
that one is pretty cool. I just like the idea of it. So like you just have like a particle like coming in and just it's still experiencing relativistic effects. So it just comes in blasting and it didn't even know it was alive. I think. Sorry, Z. But I just
No, that's
imagine like your other brothers and sister particles, just kind of come in and just like
my brothers and sister particles, my
they
twins.
they just come in and then they just get detected. They're just so quirky, if you will.
That is true. That is true. I
And
guess
that goes into
my
the quantum
answer
realm
to this
stuff.
question is I actually had to search up what next gen gravitational wave observatories would be, and I came across this one called Cosmic Explorer. It would have 40-kilometer arms, and for context, the LIGO detectors have 4-kilometer arms, so it would be like 10
40?
times as much, and it would
Why?
be able. I mean, it's intense. It would be able to trace mergers back to the earliest eras of star formation, so really far back. And what was really funny is that when I was searching this up, the first thing that popped up was this Cosmic Explorer album by the Japanese girl group Perfume. I'll have to give this a listen. So
Nice.
I that's another bonus.
That's cool.
Yeah. Um, so somebody asked, why are binary neutron star mergers so rare? I think neutron stars in general are kind of rare objects to begin with, and also, it's kind of hard to detect these mergers because neutron stars are much smaller than black holes. They are formed when stars that are less massive than like the precursor to black holes collapse. Um, and so that gravitational radiation would decay throughout the universe. So that is sort of the answer to that. And then the final question that we have is manipulating gravity to cheat faster than light travel. We got a lot of questions about this. Is that possible? I've talked about this a few times before, and unfortunately, faster
Mm,
than light travel is not possible because, as we learned in one of the postulates for relativity, the speed of light is the ultimate speed limit of the universe. And if we were to break that, we would also be breaking causality or the idea of cause and effect. Um, for instance, like if a jar were to shatter, like you wouldn't be able to go back in time and like see the jar like reassemble itself, right? In
mm,
a similar way, the speed limit of light ensures that causality is preserved, and I talk more about that in my special relativity series.
it's
I just wanted to quickly skim through these questions as we're going through on time. But Aleph, is there anything you'd like to add?
with that time reversal stuff, like is that not true in the quantum space? Because I remember like one of the biggest postulates, one of the biggest issues about quantum is that like it describes things very well in a quantum scale, more or less, and then you don't know the bridge between quantum and then reality, right? Like when do things like start collapsing around us that we can't reverse things? Because quantum,
Oh,
you can reverse things in a quantum sense, but so when things like move around and stuff like that, you can do that. It describes it, no?
yeah, I have to be honest, I'm not too familiar about this like the limitations and the possibilities of this like reversal concept. I have heard of like time reversal symmetry before.
Mm,
But one thing that may be interesting is the idea of potential faster than light communication, which is through this idea known as entangled particles.
mm,
It's basically that if you have two particles, they are entangled, and you were to put them a very large separation from each other, and you were to observe one of the pair, um, then you would be able to determine what the other pair is, and that would basically be able to break the speed limit of the universe. But there's a lot of like caveats to that, and I think it's a very active area of research for sure.
pretty cool. Pretty cool. Okay.
Yeah, and that's our presentation, it seems.
All right. Woo!
Yay!
What I can say I'm a general expert in general relativity. I think.
A very
Gosh.
general expert.
Would you believe me if I said I really didn't know anything like about a week ago?
Wait, I think everybody should give Aleph a round of applause because I remember I was on X and you had taken a photo of your whole setup, like studying all of this stuff for our collab, and I just
Oh
really
yeah.
appreciate that. It's super, super cool. And at the end of the day, this is all learning experience. So I hope you guys also learned something new as well.
Yeah, I gotta emphasize. Seems like some of you guys had thought that I was a PhD student. I am not. I am merely a bachelor, probably an overqualified bachelor. But I am going back to school. That's the whole point of VTubing, is that I'm gonna be studying. I'm doing some cool stuff, and I just want to cover a bunch of cool topics, cool things. And hopefully go back to grad school under maybe a specialty. I have no idea when. But definitely this year is gonna be the big year. So I will take some time away to focus on some of that.
Well, I'm really glad that you're able to do VTubing on the side as well. And I mean, honestly, it learning is super, super cool. Being in school is super, super cool. And yeah, I talked about this on the last stream. Like, it's really never too late to learn anything. And I mean, I also learned quite a bit, including how to pronounce some things that I've been pronouncing wrong my whole life during this collab. So I'm really glad we were able to get this all together.
Yeah, no, and you know, stars align. It just happened to work out. So, yeah, very happy to I'm very happy to try this, and let's do something else again in the future. I am very much inclined to. You see what I ended up putting effort into. I can definitely make some cool things. So I'm willing to make it.
Yeah, no, and everybody, I already shouted out Aleph on Twitch, but if you're on YouTube, the link should be in the description as well. Please go give Aleph a follow. Um, and yeah, Aleph, I was wondering, did you want to raid anyone in particular? I'm looking on my
Oh,
side here, and it looks like we see EJSA's doing Kerbal Space Program for an Ares 1 style rocket. Um,
let me see.
wait, this is so funny. We have Stephen Wolfram. The man, the legend himself, doing language design in Wolfram. Wait, I think we have to do that.
The illusion of choice. Sure, go ahead.
We
Whatever you
have
want.
to raid Stephen Wolfram, guys. Wait, you obviously know who Stephen Wolfram is, right? From
Sure.
Wolfram Mathematica?
The John Wolfram? No, I do not. But
Wait, I think it's Stephen Wolfram. He invented the Wolfram computer science language, Wolfram Mathematica, CEO of Wolfram Research, and apparently also Twitch streamer.
oh, really? That's so weird. I didn't even know that. That's interesting. Yeah, sure. Why not? Let's go ahead and do that.
Uh,
I'm totally down for that.
Crazy lore drop, but I've actually met him in real life, but I don't think he will recognize my my channel, of course.
Well, we could just what's something we can raid message with? What's something we can talk about?
I typically have my speeding at sea. This is a Z raid, but I think
Yeah, we could just say
I think it'll be funny to do it.
yeah,
Rating
whatever
this,
works. I don't have a raid message. I got to figure that out at some point.
I think it's going to be a very professional stream, given that they're doing like, wait, let me hop in and they'll be discussing improvements and functionality for the Wolfram language. Alas, I think it'll be funny to do.
Yeah, okay, sure. And I'll follow him right after. So that'd be cool.
All right, cool. Well, thank you all so much for joining. I feel like my voice has been getting better throughout this stream as well. Just one last announcement. I might be doing a stream on Thursday, so keep an eye out for that. And yeah, any last announcements, Aleph?
I'm probably not gonna stream for a while, for a minute. I haven't done. I've been incredibly busy with like real life stuff, with work and stuff. So the fact that I put so much effort into this, I'm gonna take a quick break. So probably like have one stream next week, and that's it.
All right, sounds good. Well, definitely take all the time that you need. All right, I'm gonna have my ending screen in a few, but thank you all so much for joining, and I will see you all soon. Stay happy, stay healthy, and keep learning. All right, bye
All right.
bye.
Bye
Bye
bye. Bye bye.
bye.
Have a good day. Bye bye. Bye bye.
All right, I just muted. Let me raid. Oh.